In these lectures, we have been exploring the power of a few simple ideas. So, the simple ideas are the equality sign, units, and the use of symbols. By using these simple ideas, we have been able to look at a wide range of things. At one level, you had the equality sign showing up as the equation of motion. The force was equal to mass into acceleration. Then in other examples, we found we had to use imagination and use our insight to suggest how to model a star, and to use ideas like the Euler Theorem, where the equality we used in a different way. Now, today what I would like to do is to go back to one of the starting things, which is geometry, and look at the idea of equality and how it shows up in a number of cases. And this will lead us to a different type of geometry, which is called topology. So, let us start by recalling that Euclidean geometry, which we looked at, in Euclidean geometry, the basic unit of equality was, as we said, the idea of congruence. And the basic objects were triangles. But as we found out that this whole system could be replaced by an algebraic description. And there the idea was to use coordinates. And we had an x axis, a y axis, we had to pick an origin, and we had to pick a unit. So, once these were done, then a particular point if I had a point here which had x 1 y 1 and a point here which had x 2 y 2, then you see the geometrical object in this picture is this directed line segment. It goes from 0 to x 1, which has a direction, it is going from here to here, which is of length r 1, and this goes from 0 to that point, which has length r 2. But using coordinates, we could work out all the properties of a triangle formed by this system. For example, if we wanted to work out the distance between this and this, then what we could do is use Pythagoras' theorem, and what we could show is this distance d the square of the distance in this way. It is easy to prove this by joining these things and looking at this little right angle triangle. So, we can find the distance and we can find the angle between these two lines. So, this is the distance between these two endpoints, and we can find the angle as cosine theta 1 2 is x 1 x 2 y 1 y 2 over square root of x 1 squared y 1 squared So, what we find here is that we do not really have to look at the picture, we do not have to think about the picture, we just have to look at the different coordinates, and if you want to know the angle between things, you have a formula for it, you just put in the numbers for the formula and you get the answer. So, from this point of view, once we use coordinates, Euclidean geometry is really a system of points in a 2 dimension in the example, in which a distance function is given and an angle thing is given. So, the geometry in this case is just, you have to tell me, you have to give a distance function and you have to give angle functions. Even this is not necessary. Once you have the distance function, you can figure out the angle function. So, the space, Euclidean space, 2-dimensional Euclidean space is points and a distance function. So, the distance function is given by Pythagoras' theorem, right. So, this is the standard geometry, and it is quite easy to generalize this to 3 dimensions or to n dimensions, it does not matter. All you have to say is that here we have x1, y1, x2, y2, in 3 dimensions it will be x1, y1, z1, x2, y2, z2 and so on. So, there is a easy way of generalizing geometry, and for each case we can define the distance by this. This distance function d between 2 things, the distance function has a number of properties. The first property is that this is positive. It is only 0 when x is equal to y. Okay? So, the distance is when x and y are the same points, the distance is 0. The second property is that d of x y is equal to d of y x. It does not matter how you are doing it. Third property is d of x y plus d of y z is greater than d of x z. So, these properties can be easily checked for the distance given here. However, if I construct any function which satisfies these conditions, that will also give you a distance. So, there is an immediate generalization. So, what we have done is the notion of equality, the notion of what do I mean by a distance is given by equality. So, I am still sticking to coordinates, but given coordinate points, the way I define the distance can change. So, let me give you a practical example. So, this is a nice picture of streets. So, these are streets which go like this, horizontal and vertical streets. Now, if I want to go from here to there, I cannot travel like this, there is no road. So, my distance could be, if I take a taxi, it is a taxi fare, and the taxi fare depends on how much distance I travel. If you have a system like that, then it will depend. So, the distance between A and B, the distance is this plus this, or it can be like this to this, or it can be like this, 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 many distances, right. Then there is the shortest distance which one can construct, and which is like this. So, this would give a geometry, that means a way in which points and distances are introduced, and it is called the Manhattan geometry. And for this Manhattan geometry, things which are equally distant are from here are this point, this point, this point, this point, they are the same distance from the center, but this is not equal to this distance, right. So, these things are same distance, right. So, this will define a circle. So, in this geometry, points which are equidistant, if I think of this as a circle, and if you work out the circumference of the circle, right, and you can work out the value of pi for this geometry. So, this is actually a realistic and useful geometry to have if you travel a lot by taxi, okay. And the assumption is you pick a time when there is no traffic jam. So, under those two conditions, this is a useful geometry. So, it is an example to show that the idea of a distance can be varied, and all you have to check is these general conditions. A space, which means a collection of points, right, in which you have a distance function which satisfies these conditions, is called a metric space. So, this is one direction of generality. So, you are saying that I give you a certain structure which is points, and there are different ways in which I can have equality. So, two points have the same distance from something, they equally separated from a certain point. It will depend on the choice you make. So, the choice depends on the function, it changes. Let us look at a relaxation of this idea of similarity, similar triangles. Instead of having congruent triangles, we can have similar triangles. So, you have similar triangles. So, this triangle is equal to this triangle. If this is alpha, this is beta, this is gamma, this is alpha, beta, gamma. So, two triangles may not have the same lengths, right, but if they have these same angle, that is they have the same shape, then you in certain problems you might like to consider them the same. So, the notion of equality has been changed. Things are equal when they have the same angles, and so that means that if I describe this in terms of coordinates, what this means is d of x y is equal to d of lambda x lambda y. Oh yeah. So, what we have here is this distance is supposed to be the same as this distance if I scale them. So, this has an extra property. So, it satisfies these conditions, but then you impose the additional condition. Once you have got the imposed the additional condition, then you see the angles do not change. Remember that the cosine of theta was x1, x2, plus y1 y2 over square root so if I change x1 y1 goes to lambda x1 lambda y1, x2 y2 goes to lambda x2 lambda y2, then cos theta does not change. Okay, because this gets multiplied by lambda, you have lambda squared from outside, you get a lambda from here, a lambda from there, and the lambdas cancel out. Here this is y. Yeah, x1 squared, y1 squared. Thank you. Okay, so the point is that from the coordinate geometry point of view, this feature of similar triangles is easily implemented. Okay, so this tells you again the way the idea of equality can be modified and give you greater insights into different problems. So let us now apparently leave what we are doing, right, and then come back to it. And this step is necessary because I now want to introduce a completely different notion of equality, which was discovered by the famous Swiss mathematician Euler. So let us first start with pictures like this. So what I have done is I have drawn regular shapes. They need not be regular, but I have drawn regular ones which have 3 sides, 4 sides, 5 sides, 6 sides. I can draw 7 sides, 8 sides, and there is no end, the infinite number of things. I can keep going. Okay? And from the point of view of geometry, they are completely different. There is no way geometrically that this one has any relationship with the other. You can construct the others using triangles. Right? So this is the basic building block, right? But they are geometrically distinct. So these are okay. So what we will do is we will look at these and follow Euler. What Euler did, I do not know why he did this, but he did something extremely simple. He counted the number of vertices here. So this is V for the 3 dimensionals 1, 2, 3. We counted the number of edges 1, 2, 3, and counted the number of faces, which is 1. Right. So here you have a 3-sided figure. All you have done is I have counted 1, 2, 3 vertices, 1, 2, 3 edges. I do the same thing for this. V4 is 1, 2, 3, 4, edge 1, 2, 3, 4, face 1. V5 1, 2, 3, 4, 5, E5, 5, F5 is 1. this kind of boring, maybe exciting depending on your point of view, list can be continued, and you expect for V n there will be n, E n will be n, and F n is 1. So, then what he did was he looked at the combination V minus E plus F. So, the number of vertices minus this plus that. So, in all of these cases you see this is equal to 1. Right. So, whether here V minus E plus this, V minus E plus this, V minus E plus this, V minus E plus this is 1. So, he said all of these pictures are equal. So, any picture which has this list is equal. Okay. So, now why is that going to be useful? Well, we will come to that in a minute, but for the moment this is an interesting observation, that for thousands of years people had studied geometry, and as far as we know, no one had looked at this particular simple feature. Let us go down one dimension. So, before we go down one dimension, no, I go down one dimension. So, in one dimension I have little line segments right. So, again I follow Euler, and I say the V for this thing which has V2 is 2 and edge is 1, V3 is 3, edge 3 is 2, V3 for this is 4, edge 3 is 3, V n is n, edge n is n minus 1. So, we find again that V minus E is 1, okay, in all of these cases. But now let us do a little variation. Now what we do is we add like this. So, let me keep that separate. So, what we have done is we have still edges, there is nothing in the center. What we have done now is we have introduced a loop. So, this time the V is 1, 2, 3, edge is 3, and so V minus E is now 0. Okay. Now, if I put in a loop in any of these, one can check that this happens. Let me put 2 loops. So, this time I have check holds for all figures with 1 loop. Now, I make 2 loops. Okay. So, this time the V is 1, 2, 3, 4, E is 1, 2, 3, 4, 5, and V minus E is minus 1. Okay. If I am very quick, I can make a conjecture, and the conjecture is for 1 loop this is 0, for 2 loops this is minus 1, for n loops, V minus E should be equal to minus n. Okay. So, this is a very simple thing which then you can prove this, that this is true, right. So, if you have a wire net, if you are a fishing net, right, and if you just count the edges and so on, you will know how many loops there are straight away without having to count the loops separately. So, it is a way in which you are dealing not with the detailed properties. If I distort this, right, if I move this and make this, if I distort this to keep these things but have a like this, like that, and these are still edges, right. It is unchanged by any of these modifications. Okay. So, he had stumbled across something which seemed to be very robust. It was capturing some very special property of a geometrical figure. So, let us go up one dimension now from 2 to the next higher dimension. So, let us now look at closed I will not draw the others, but one can draw. So, this is you are pasting a certain number of triangles, you are pasting a certain number of squares, and at the end, right, you are getting something which is closed, which has no boundary. Before, when we were doing this had a boundary, but this time there is no boundary, it is all closed, right. So, this is a closed surface. So, let us again count. V is 1, 2, 3, 4, edge is 1, 2, 3, 4, 5, 6, and face is 1, 2, 3, 4. Okay. So, it is much better to have a concrete model, then you can do it easily. For this case, this is for the triangular thing. So, I will put 3, and this is for this thing. This is 1, 2, 3, 4 here, 1, 2, 3, 4, 5, 6, 7, 8. Edge is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The number of faces is 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 faces, right. So, again what we find is V minus E plus F is 2. So, this result, this is called the Euler characteristic. Right. And so, the thing is that what this is telling you is if you have a closed surface which is like a sphere, you see you can blow this up and distort it, this is not going to change, right. So, all of these are ways of tiling, this is tiling a sphere, okay. And when you tile a sphere, the answer when you do this is equal to 2, okay. So, from this I will now prove that if you want to make a football made out of pentagons, you will need 12 pentagons. So, let us do it. So, the way I will do it is I have box, right, different boxes, and the boxes I will have triangles, squares, etc. That means I will have if I have a triangle, we know that for an n-sided figure, the number of vertices we found was n, and the number of edges we found was n. We just did that calculation. So we know that kind of result. And suppose if this time we say if there are n faces, n, so for each face, right, for each face you have this. That is, if I draw an n-sided figure, like here's a triangle, it has 3 and 3 edges, and there's one of these, right. So each one of these, so let me call the number of faces in other words, I have a box full of these shapes. Fn is a number of these things that you have, which is like n. We have n of these, Fn. Okay, so now what we want to do is to glue them together so that all the edges disappear. So the E, the vertex total, the edge total, and the F total, when I've glued everything together, right. So how do I do that? Well, start with the edge. I have to glue two edges together. So if there are n of these, half of n, summation over n, all the possible things you have, that's the total number of edges. For the vertices, I have to make a rule that suppose I have a thing where you have 3 vertices come together. You can have other rules. So I assume I'm gluing together 3 vertices. So this will be equal to 1/3 n summation n. Okay, and Fn, let us suppose there are n of these things. So for each one of them, you have this rule. So then Vt minus Et plus Ft is equal to summation over n half n minus 1/3 n minus n. This Fn, for each one of them you have a thing like this, right. I mean there could be n of these things. So we are saying that so for each face this is the case, right. So what we are saying is that I take a face, an n-sided face, right, then I have so many, when I've glued them together, right, the net result is I'm generating let me write it this Fn that is better. Okay. So for each face there are these and the total number, this is the thing, right. So that's what it is, right. So what we have is this expression gives you, yeah, it's plus 1. Yeah. Yeah. So this is the formula which we have, and so if I multiply this by 6, but this thing for a sphere has to be 2, right. So if I multiply by 6, I get 12 is equal to summation multiplied by 6. So that is 3n minus 2n plus 6. So that is equal to into Fn, right. So what we find then, this is summation over n For vertices, this should be 3. Vertices is 3, right. So, this is 2, this is 3, and this is then 6 minus n f n. Okay. So, if I consider, you see, this has to be positive. So, n should be smaller than 6, otherwise this becomes negative. So, if the minimal number is when I take n is equal to 5, a 5-sided figure, then what we find is that 6 minus 5 is 1, and we get from this expression 12 is equal to f n. So, you need 12 pentagons to form a sphere. So, let me go through the steps again. So, the idea is you want to glue together different size figures to form something which has the Euler characteristic of the sphere. To do that, I have glued together different n-sided figures. How do I glue? I glue 2 edges together, and so that means for each of the faces there are n sides, n edges, you sum them and take half, that is the number of faces. To glue the vertices, I have a rule that I glue 3 vertices together, each f n has n, that is the total number, sum divide by 1/3, and f n, the total number is just sum f n. So, now v minus e plus this is vertices is this 1/3, edges is this, and the faces is this. So, when I do that, I get the formula, this formula. It tells you that if you glue 3 edges together to close the thing, then this condition has to be present. So, for example, if I put a 7-sided figure, this will be negative, but I can cancel by having a 5-sided figure extra. Okay. So, I can make things more complicated. So, the buckyball is an example where things can be more complicated. Okay. So, the minimal number of similar sized figures which will work will be n equal to 5. So, then 6 minus 5 is 1, and then this f n, there is only one term, this is f 5. So, then f 5 has to be 12. So, this shows that from starting from extremely simple idea which is completely observational, one can derive a result which is not so obvious. Okay. And the reason for the 12 is because of this constraint which comes from rubber sheeted geometry. So, the geometry in which you can continuously deform is called rubber sheeted geometry, and that is topology. It is called topology. Okay. So, what I will do is spend a few minutes discussing how to formulate this concept operationally. You see, what we did for geometry was we introduced a space which we called Euclidean space. So, what I want to do is to give you a general notion of how to formulate the idea of a topological space. Okay. For the geometrical space of Euclid, we said if you are given a collection of points in a coordinate system, and if you are given a distance function, that you are on your way, you have a Euclidean space. Now, we are talking about a geometry in which the notion of distance is useless, because you are continuous deforming, it is rubber sheeted, you can continuously deform it, you see. So, the way out is to introduce objects which are invariant under deformation. For Euclidean space, the distance function introduced is invariant under translations and is invariant under rotations. So, it does not change. If you rotate a triangle, it is still a triangle. If you translate a triangle, it is still a triangle, right. So, the building block in Euclidean geometry respected the underlying symmetry. For the topological space, we have to find some notion which is invariant under continuous deformation, and the simple object which has this property is an open set. So, in 2 dimensions, if I draw a circle or if I draw a thing like that and I say this is all the points not on the boundary, which can be very close to the boundary, right, but are never on the boundary. Okay. So, they are open, there is no boundary, there is no limit point, right. So, now if I continue to deform this, those points will remain, they will not get modified. So, you have a notion of an open set. So, instead of points, if I want to make a topological space, right, the topological space building blocks are a collection of open sets, right. And in Euclidean, you have to give me the points and then the infinite number of points, but you have given the points and the distance you are on your way. Here you have to give me the collection. So, you have to list open sets and they must include the null set and X. Okay. So, that means I tell you the topological space is X, the X itself has to be an open set, right, and there is a null set which in a perverse way it is also an open set. So, assigning a topology, the simplest or the crudest way is to say I have only 2 sets, X and phi, null set is phi. So, each time I give you this list, I give you a topology on X. There are many ways of doing it, you see. The open sets have to satisfy some axioms, rules. One rule is the union, if you put them together of open sets, is open, and 2, the finite intersection of open sets is open. So, if here are the sets, right, this is U1, O1, O2, O3. If I take the union, they are this, and if I take the intersection, that is the intersection, and that is also in the thing, but it is finite intersection, right. So, this structure gives you the notion of a topological space. So, a topological space has building blocks which are invariant under continuous deformations. Okay. Sadly, the first thing you want to know is if I give you a topological space X and a topological space Y, right, are they equal? I will not go into the technicalities of it, but the equality means that you can continuously go from one to the other and back again. That is the notion. And so, they are said to be equal or homeomorphic, right. Unfortunately, there is no way, no algorithm for deciding this. So, the structure is can be introduced, and the reason I have spent some time on this is because when reading books on topology, these are introduced without any motivation. I hope this gives motivation, so one can understand why you have such definitions, right. And the subject is a very powerful subject. For example, many of the standard methods of the subject were introduced by Poincaré, and he invented them because he wanted to study the stability of the solar system. For the stability of the solar system, you do not need to know the precise location of all the planets. What you want to say is, at time t, if they are in some region, at the time t plus delta, which may be 10 million years, right, is still within some particular region, and that is a qualitative kind of result. And in order to do that, he invented many of the tools of topology that he needed. So, it started from this very practical thing. It has then grown and grown and grown, and it is now recognized that in fundamental theoretical physics, in condensed matter and in particle and high energy physics, it plays a very crucial role. Now, there is a story that the famous physicist in the US was asked in the 70s what kind of topics should be left out for physics students, and he said, well, you can leave out topology, and he was a Nobel Prize winner. So, it tells you that as time progresses, people begin to understand the power of abstract ideas. In fact, the famous British philosopher Whitehead said that as soon as you start looking at more and more practical problems and more general practical problems, it is remarkable that it becomes more and more important to use abstract methods. Thank you. Yeah. Yeah.
That idea of that's of course, I have to tell you, that's a phase rule that you wrote down.
Yeah.
F is equal to c minus p plus 2 is isomorphic to this relation that you have,
yes.
the edges and the.
Yes.